Okay, so here we are back at the STM32Cube MX tool, but here in this processor, which is this processor board right here, what we'll do, put a link in the bottom for where you can get this processor. We hope to do a lot of things with this, including maybe some graphics there on the LCD that's already on the board, and so we'll go through a lot of detail on the functionality of embedded processors. Okay, digital to analog conversion is usually done in the processor for 12 bits, and if you need more than that, you are going to have to go to external. And typically, these are not really fast, so their conversion rates is pretty slow. If you need to do high-speed stuff, you won't be doing it on chip. You can see here, right here, that I have selected output 1 for the configuration, and output 1 is right here on PA4. So that's where the output of this is, and we're going to go take a look at the manual in a minute. But before we do that, I can't stress enough, I have to tell everybody over and over, you have to look at the errata sheet to see everything you do, if there's any functionality that's messed up and that you have to work around, or some issues. You need to know what those issues are, because if you don't, you can really spend a lot of time going nowhere. Okay, so let's take a look. This is my silicone limitations for the processor, what I would call the errata sheet. Let's see what they call it. Yeah, see, they call it the errata sheet. So we're going to take a look at the DAC. See, SPI bus, I2S. Interesting. Might have to also talk about that. CAN bus, someday we'll get to that. Let's see what else here. Here we go. Here's the DAC, peripheral limitations. So we'll go to there. Oops. Oh, we kind of have a problem here, huh? So let me move the video out of the way for a moment. So it says here, if the DMA is not fast enough to input the next digital data to the DAC, as a consequence, the same digital data is converted twice. Okay, I understand that. So basically it's saying that if you put data in and then the DMA is DMA'd again really quick and you haven't changed it, it's going to put the same number in. So in other words, DMA transfer may be timer based, or there may be some issue with that. Now, I'm not going to use DMAs for this. I'm just going to stick a number in, right? I'm not going to do anything really super fast or anything like that. So we're just going to stick a number in. What we're going to do, stepping through and debugging, is so slow to real world that I won't run into any troubles. So that's any issues to do with the DAC. Now, if I go here, this is the manual. And we look for the DAC. It doesn't say a whole lot there. Here we go. Digital analog converter, page 43. There we go. Now let's see, put my video back here. That doesn't seem to cover up the section that I think is important. So it's basically saying there's two 12-bit DACs. They're buffered. Okay, that's cool. You put a number into essentially a register, and it gets the mechanisms of the hardware will actually just run that through the conversion, and then it's sitting there. So it's not something where you have to hold the number into that output. There's two DAC converters. In other words, there's two channels that come out of two pins. As you can see here, we just have the DAC clicked onto output 1. If I were to select the second one, and then would come out output 2, which is PA5. Okay, but we're just going to use the PA4 right here. This gives details about how the DMA or DAC process is done. It's necessary to have an input voltage reference. This is important. So you expect that you want to see this VREF right here. You want to see that on the schematic the hardware guys make for you. Okay, you definitely want to see that the voltage reference is there, because if it's not, then your output isn't probably going to be the right voltage, and it won't do what you're expecting it to do. And since we're going to allow the system to generate this for us, let's see, generate code, which it will do for us. Okay, so it has brought up the completion dialog, and basically you either open the project. This will automatically run your system workbench, or you can just open the folder. If you open the project and it fails to open, that was a problem with your installation. You may want to install the system workbench again, but you can always just open the folder. I'm going to do open the folder this time, just so you can see. So here's my project. It's all here. So the tools are going to come up on a different screen, and so what I'm going to do is I'll move it over to this screen once it comes up. It's running right now. Okay, so the system workbench has come up, which is Eclipse. It's all customized for us by STM. And what we'll do is we will get rid of this so that that doesn't get in our way. Now we'll take a look at what we have in main. So I haven't typed any code in. It's all being created by the tool for me, which is great. You know, I don't want to spend my life trying to create all of this, you know, clock configuration and the ADD configuration. I mean, that's a lot of stuff, and you know, to get all this right the first time when you're doing this blind is not an easy thing to do. So I'm very happy for STM to do it for me. Thank you very much. It's worth the price of admission, I believe, because you can waste easily 3, 4, 5, 6 weeks, and in reality that's a lot of money, and you don't want to do that for even if it's yourself or a company. You don't want to do that. So here's the initialization of the DAC. We saw that in main right here. So this is the first function call. Here's main. Here's the DAC init, which is what we're going to go look at. Basically, this is all the initialization code for the DAC. So once this is called, the out1 is configured, ready to go to start putting functionality or putting voltages out on the pins. Now, the next thing we want to know is we want to see what DAC functionality we have. The nice thing is that they create all the functions for us. So we want to go in here. So DAC init we'll have to call. That's been called. We don't worry about dinit. Okay, so it has a start. So the importance here of a start is that the process of the conversion is actually a process, so it has to be given a value, and then it has to be started. So we have to know about start, and we have to know about stop, which should be the next one. Stop. And we probably won't use stop because I don't have a reason to actually stop it. We won't be using DMA in this video. So get value from a DAC, interrupt, configuration of a channel, set value. So this is the function that we will use to set the value. And as you can see here, there's several inputs that are required. Some of this has to do with if you're using 8-bit or 12-bit, and bit alignment, which has to do with whether you're little endian, big endian. So what we're gonna have to do here is we're gonna use this set. We have a specific channel, which the channel is defined in the start, and then we'll just set value. It'll go through all this code, and then when the output, we should be able to see that the output changed. Okay, so now there's details that we're going to want to be knowledgeable about. We're going to have to study and understand and read about. So the input here is this HDAC, or this handle type def DAC handle. So that's a structure. The channel, which we're going to use in channel 1. The alignment, so we have to learn about what alignment is, and then the data we want to actually send. And even though this is 32-bit data, we're only using the first 12 bits, right? So alignment, 8-bit, right, we're not going to use that. 12-bit, left data line, right data line, we're going to have to understand what that is, okay? So what could help us understand what this is to take a look at, so that's what we're looking at is this file right here. And there's a related H file. So let's take a look at the related H file, which is this one. And configuration structure, they're taking care of that for us. DMA state, we're not doing DMAs. DMA error, we're not involved with DMAs. Error codes, we probably don't have to worry about transfer because we're not using DMA, we're not using interrupts, okay? So here's the first parameter that we have to have. And I think the first parameter, the only thing we really need to pass in the first parameter, since we're not using DMA, we're not using any of the fancy transfer hardware or anything like that. So I think the only thing we need is the instance. Since the software in main has already initialized it for us, we may have a variable there that we can make use of that's already got this filled out for us. There's all the errors. Oh, here we go. Channel 1. Nope, we're not doing DMA, so we don't need DMA. Peripherals, memory fit, yeah. Oh, here's alignment. Alignment for DMA. Let's keep looking around here, see what we find. Lots and lots of stuff involved with DMA, and that's because it's pretty complex a lot of times to do DMAs. So I don't think there's a whole lot left here that's going to help us out with what we're doing. Here's the functions we're going to use. Lots of DMA. We're just going to use the variables that the parameter parameters and functions we saw here at the top. So these are all just enums or structs or defined variables. That's all we have here. So that's good. So we need to call this function. We need a handle of this structure, channel 1, we know that. The alignment, I believe, is going to be 12-bit right. And then the data that we're going to put in, which is just a number. That's all it is, a number that's within 12 bits, which is 4096. Okay. Okay, so now let's study carefully the function we're going to call, the set value function. it's interesting that it returns status. The status is always okay. So I guess there's no expectation anything's going to go wrong. And for our case, it's not going to happen. You're going to have to really run fast. I don't think you're going to outrun the actual DDA conversion, but you have to really run fast to like make this routine mess up. Since we're going to be stepping through just to show you the functionality works, I'm not going to worry about this functionality failing. If you're trying to create like a wave generator or something like that, and you're jamming numbers as fast as you can calculate into it, maybe you might have some problem. Okay, but for what we're doing here today, we're just going to set a value, go take a look at it to see if the value is actually set. And maybe what we'll probably do is we might hook it up to something that somehow we can read it. So I can show you that we successfully set the DAC. Okay, so we're going to take a look at how this function works. The funny thing is, the first thing I see down here is it always returns okay. I don't think you really have a problem with that unless you're like banging the set value super fast, which you should really never do. Either have a delay or a timer. You shouldn't be hammering it really fast, and it's not going to be able to keep up with that. So I don't think we're going to be doing anything that's fast. In fact, I'm probably stepping through, so it's super slow and real compute time. So basically, we want to call this function. Turns out that the start function that I talked about earlier is not needed because we're not using any fancy features, no interrupts, no DMA or anything like that. So let's take advantage of this and make a copy of that. Go back to our main. And what we're going to do here is we're just going to remove the types. Should I do this the easy way? Okay, now the interesting thing is that I see there's no squiggly line underneath the HDAC. Thank you, SD Micro. You did it for me. And it turns out what that is if we look at the DAC init, you see it has an HDA instance that is set. Well, that's because it's right here. Okay. Thank you very much. Took care of it for us. And since we've initted it, it's already got the minimum necessary to make a function call to. So now we just need to set the channel, the alignment, and the data. So let's take a look at the function again. See what there is to learn. So they're definitely going to make sure that your parameters are set. And if they're not, they're probably going to, this is probably a macro that's going to return. It's going to return something. Actually, right now it says void, does nothing. But basically, the instance is there, so we can make use of that. It'll look at alignment, set alignment, and then set the data. Done. So the instance is basically the address of the DAC itself. Okay, very simple. So let's go back here. We want to set a channel, so we can see that it's 1. And if it's not 1, it'll be 2. So that'll be the else. There's only two. So there's our second parameter right there. Okay, and then we'll look at alignment, which is passed in. Okay, so I think we're going to have to look at the .h to find alignment information. This is the DAC.h. That's the struct for the output configuration. Here's the DAC channel 1. Here's alignment. So I believe that 12-bit right is what we're going to start with. I think that's the correct one. If I'm wrong, we'll find out. Things won't work. So I'm going to set that alignment. And so now we need some data. Now, this data is an unsigned 32. I don't know why they had to do that, but fine. We'll just make the number. Remember, it's from 0 to 4095. So we're just going to make it 2048, which is about halfway. See if we get any. Yeah. Okay, so it's pretty happy with it. So when we debug and we come here, we're going to set that value. Now the question is, how are we going to know that it actually worked? Well, we know that here, probably it doesn't say the voltage. So I'm assuming we can look at the manual. We can take a look at the manual. And anyways, I don't see it right now, but I think what's going to happen is the processor is running at 3.3 volts, so the output is going to go from 0 to 3.3 volts. And 3.3 volts represents the 4096. At 0 volts is 0. So if we put in here, if we put in 2048, that's almost exactly half. 2047 is probably half. We'll see half of 3.3 volts on the output. So now the question is, what do we do next? Since we're going to do this through debugging, we're going to step. I think we'll bring it down to 0. And then we'll do it again and bring it down to, or bring it up to 4096. Okay, now it starts at 0, so there's no such thing as 4096, 4095. That's the maximum. Okay, so we should see half of 3.3, and here we should see 3.3 and 0. That's what we should be able to measure on the output pin. Okay, because I'm going to assume that on the board that we're using, the reference is already set up correctly. They wouldn't send us a board that's not, ready to go. Okay, so now we need to test this. We have our code. I'm basically going to set the DAC channel 1 to 2048, which is the center of the range. So it'll be the middle of 3.3 volts, 0, and then 4095, which is at the top of the range, which will give us the full range of 3.3 volts. Okay, so how are we going to test this? Well, if you remember, everything was put out on PA4, and I can bring that up, but first I'm going to show you, I just looked for the board, STM32F4 discovery datasheet. That's to this board, explains how this board is connected. I went to that link. This is the link right there, and then it downloaded a manual for me. This manual basically has everything I need in it. I just went through some of the pages. Specifically, what I was looking for was to come to this drawing, which now I want to hunt for PA4. And if I zoom in, PA4 is right here. So this is PA4. This is probably PA5, 6, and we don't know what that one is because, basically it changed to a different row on the processor. So anyways, this is PA4. So we are what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pins down from the top. So here's the board. So that would be, this is the top, right? I mean, this is how it's oriented. So this is the top on this side. We just count down to that 11th pin, and that's the pin. Just so happens right here at the top is ground. So we can put our voltmeter on ground, and then on the 11th pin, and we can see if we see changing voltages. Okay. So that's how we found we're going to take a look at the output. Okay, let's verify that's PA4. We're going to go back to our CubeMX, which generated the code for us. And right here, PA4 is DAC output 1, which is the one we've configured. It's on pin PA4, and that is brought out to this pin right here, which is 11 pins down. Okay, so now we got to set up for testing this. Okay, so I plugged in the board, turned it on, and interesting, I guess was what we expect. The pin is at 0. So let's run the code. We want to debug. Does the build, brings it up into main. So we have a task started and it runs. Okay, here we are inside that task. And so we're going to set it for half. Let's see for half. So let's step over that. That should set the DAC. Okay. And then 2.8. So 0, 1.4, 2.8. Not what I expected. I'm going to run this test again, maybe with a different alignment, because I'm not sure that that's the expectation I would have. And it's close to 3 volts, 2.8, and half was 1.4 and 0, 0, and that's good. Initialized to 0. So it's all the things that I expected it to be, but I'm just sort of wondering if it should be closer to 3.3 volts versus 3. I don't, well, I guess look at this right there, 3 volt power. So the processor is running at 3 volts. Okay, so pretty much, it's just a meter here. I don't have the right load and that kind of stuff, so it is what I expect it to be. So that's great. So we've proven that I can set it to center. We've proven that I can set it to 0, and I can set it to the maximum range, which is the 2.8 volts in this case. Okay, so next stop, I think we're going to start taking a look at PWMs, what they are, what they mean, how you use them, and all that kind of stuff. They're easy to understand and easy to put to use, so we'll do that next. But for now, that's a DAC, just the simplest case, which is to put a value into a DAC to see a readout on an analog. I just used my meter to look at the output on the pin, and I did get 0, 1.4, and 2.8, but it did what I expected. Happy with it. Didn't use any interrupts, didn't use timers or anything like that. Just the simplest, set a value. Okay.